Hi everyone. I know you're expecting to see Marty today. You might have noticed he wasn't at the midterm yesterday, but he wanted me to tell you all that he was in an examination room because his wife is in labor. So there will be So there will be a baby step in the world fairly soon, and yeah, I'm sure he will share pictures. He's having a girl. Yeah. I know he was thinking about naming her like midterm check plus, but I think they're gonna go with Eve. His wife won that battle. Yeah. So what that means for all of you is you'll probably be seeing a lot more of me, which, sorry, Marty wishes he were here too. But yeah, so. Okay, before we begin, I just wanted to make a couple of announcements. First off, there were a couple of people left some things in MEMOD yesterday, so if you lost a water bottle, a car key, or your textbook, please come see me after class. And then also, it's President's Day weekend, which means no lecture on Monday, which is great. This also means there's no lair on Sunday because section leaders like 3-day weekends too. So if you have any questions, please feel free to post on Piazza, or Lair and Claire will both be open on Monday as normal. And actually with more people staffing it, which is good. Okay, so let's start talking about binary search trees. So today we're going to finish up our discussion of binary trees, which we started talking about on Wednesday. And then we're going to learn about a special kind of binary tree called binary search tree, which has this nice ordering property that makes a lot of operations much faster. And so we'll code some of those common operations. As a spoiler alert, binary search trees are how the Stanford map and set are implemented. So if you were ever wondering, like, why are they so fast? Why are they sorted? This lecture is totally for you. And then we will also, we're going to basically implement a binary search tree between today and next Wednesday. Okay, so before we get to binary search trees, I wanted to talk about traversals. So traversals are like the best way to approach any tree problem. So basically with any tree problem, you're going to need to do something where you're going to need to look at the node and look at its children. So there are 3 common traversals: pre-order, where thing you're doing at the node you do before you look at any of the children; in order, which we'll see why it's called in order once we get to binary search trees, but it's basically you go to the left and then yourself and then the right; and post order, where you probably guessed you do the children first and then yourself. A different way to think about it is you can think about it, you can trace around your tree, and the way that the order you pass the nodes indicates the order you would traverse. So when you're doing a pre-order, the first time you pass something on the left side, you would print it out. So in this case, it'd be like 17, and then 41, and then 29, and then you go up here. We already printed out 41, and then go down to 6, and go up here. Sorry, pen is lagging. Well, that's what it looks like after it's done. But so basically you would go around and do like 17, then 41, then 29, and then back, and then 6, and then past the 9, the 81, and the 40. You can do the same thing with in order and post order. So for in order, it's the second time you pass the number. So we've passed them the first time. Okay, now we've passed 29. Now we've passed 41. Now we've passed 6. Now we've passed 17. Now 81. Now 9, and then 40. And then post order is when you pass it on the right side. So we'll see examples of using all 3 of these, but they're just good to keep in mind because almost any tree problem can be solved with some variant of a traversal. So whenever you need to do something with trees, try to first think about like, hey, is this a traversal problem? Which traversal should I be using? Yeah, so if you want to talk with a neighbor and try to figure out what the pre, in, and post order traversals are for this tree. Okay, does anybody want to share a pre-order traversal that they found? Yes.
42.
Okay, so 42.
So, yeah, 42, 15, and then we're going to pass 9, 86, 3, 39.
Yep, exactly. So we have 42, 15, 9, 86, 3, 39. Okay, what about in order? Yes, in the back.
15, 42, 86, 9, 3, 39.
Yes. Sorry, this should be 42. Yeah, exactly. Okay, and then post order? Yes.
15, 86, 3, 39, 9.
So, okay, I think that was almost right. So, let's see. So we passed 15 on the right. Then we passed 86 on the right. And then I think you said 3, but we haven't yet passed 3 on the right. So we go down and we pass 39 on the right first. Yeah. So 39. But everything else you said was like spot on. 9 and then 42. So if you're one, yeah. So 86 is before 9 because you process the left child before you process the node itself. So yeah, so in this case, like it's when you pass it going down, like around the bottom. So we pass 86 at the bottom before we pass 9. I know this all just seems like meaningless vocabulary I'm making you learn. I'm sorry about that, but like once you start doing tree problems, if you remember traversals, like basically all tree problems can just be written if like you figure out the traversal and then figure out what you should be doing with that node. Cool. Hopefully those match. Okay. So on Wednesday we wrote a print function, and which looked like this. So what do you think would happen if we moved the call to the print the node itself up to A? Any ideas? Yeah.
When you read it, like you wouldn't check if the node was null, so you probably hit an error where you tried to access data from a node that didn't exist.
Yeah, exactly. So if we put it up here, then you're going to see, let me also just try to make this bigger. Hold on. Can you all see that better? So if we try running this, you'll see some ugly text that basically says, that we crashed, hold on. Yeah, so it says a segmentation fault occurred during program execution. Basically what this means is you hit null and you didn't check for null and you tried to dereference null. So, okay, what do you think would happen if we put this line here at B? Is it going to be a type of traversal? Yes. Yeah, exactly. So it'll be pre-order traversal, meaning we're going to look at the node itself before we look at any of its children. See, so, okay. Put this into perspective. Apparently can't switch screens. Okay, but 55 is the root of this tree, which is down here. So it prints 59 and then 29 and then -3, etc. So, okay, what about putting it C? Is that a kind of traversal? Yeah. Yep, exactly. And then D would be everybody. Yeah, exactly. And then E would also have that same null pointer issue that we saw before. So this is basically just a fancy way to just rearrange how the nodes are printed. Which doesn't seem like it's that useful, but this is, like, it actually can sometimes make a huge difference in how the tree is printed. Cool. So, okay. This isn't, like, okay, so we have these trees. We can print them, which is great. We can traverse them, which is also great. But something that's more useful is being able to tell whether your tree contains an element, right? Because that was one of the big set operations that we saw, right, is contains. So let's talk about how we would write contains for a binary tree. So the idea is if the value is in the tree anywhere, we want to return true, and if it's not, then we return false. So does anybody have any ideas of any techniques maybe we just learned that could help us with this? Yes. Yeah, exactly. So the idea is we're still going to be looking at all the values in the tree. So we still want to use a traversal, but instead of actually printing the value, we wanted to see if the value at that node equals the value that we're looking for. So exactly right. Like I said, all tree problems are basically traversal problems in disguise. So, okay. So we know we're going to be doing, okay, we know we're going to be doing something like contains node left value, contains node right value, right? So the question now is, what kind of traversal is this? Do we want to do a pre-order where we check the node before we check any of its children, or a post-order where we check all the children for that value first and then come back to this node, or an in-order? How many people think pre-order? Raise your hand. Okay, how many people think in-order? How many people think post-order? How many people think a traversal is totally wrong? How many people think they really should not have come to class today and should have just, like, stopped at the midterm? Yeah, okay, that one's clearly the correct answer. I asked the audience. So, okay. Pre-order is a good choice because we have all the information we need. If we're looking at a node, we have enough information to tell, like, is this node the one that we're looking for, right? So, okay. Idea is if node data equals value, return true, right? What do you want to do with the calls to contains that we make of the two children? Yeah.
Do we need to put them within the
Yeah, you were like one step ahead of me. So the question is like, don't we need to wrap this all in the if node is not equal to null pointer? And yes, because we are doing recursion and we currently are missing a base case, which I know you all know that is the answer to the question. So let's see. So we have if node is not equal to null pointer. Cool. Okay. So that's good. So we avoid our base, or we have a base case. What do we want to do with these two calls to contains? Yes. Okay. So if this or this, return true. Exactly. So basically, what we're doing here is generally a good base case for trees is checking if the node is null, and then going through and like checking this value. So that's the thing that we're doing at this node, and then our post-order traversal. So we can try running it. Yep, so okay, we see 87 is in our tree, 55 is in our tree, but like 6 is not in our tree. So our contains function seems to be working. What questions do you all have about like traversals and contains? Yeah. So the question is like, why did we have to do a pre-order traversal here? Why couldn't we do a post? So let's try it out. So we get the same result. Contains continues to work, which is a good sign. Here it doesn't matter a lot in that like you're still going to get the same answer. The problem is like let's say I go to this node and I see I have the ability to know this node is the one I'm looking for, but instead of doing that really easy check, I like go all the way down to my leaf node. That's like a lot of extra work. So it's more of an optimization here. It's not something that's strictly necessary. Though like there are some functions where they like the order that you do things really does matter. Yeah, great question. Okay. Any other questions before we move on to binary search trees? So that contains function was like pretty good. It worked pretty well. Does anybody know what the runtime of this function is? So I heard some log ends and I heard some ends. So basically, I guess a good question is, will I need to potentially search every single node in my tree? Yeah? I'm seeing a lot of nods. So that makes it O n. So I think we can do better because sets are O of log n, right? You all remember this from yesterday? Traumatic experience. So, okay. Somebody ask a question? Okay. So binary search trees actually let us get to this O of log n. So currently our tree was just like all the nodes were in a random order. But if we enforce an ordering property on the way the tree is structured, we get a lot better results. So the ordering we're going to have is we're going to say, okay, if I'm at the root, everything to my left is everything smaller than me, and everything to my right is all bigger than me. And this is a recursive property, which means, if I go to my left child or my right child, those are also going to be binary search trees. So as an example, everything smaller than 55 in this tree is on this side, but and everything larger than 29 but smaller than 55 would be in this subtree. Okay. So let's see if we can maybe change our contains function to get to that O of log n instead of O of n. Runtime. Why don't you talk with a partner and try to figure out a way to optimize our contains function taking advantage of this ordering property. Okay. So I'm going to put this back as a pre-order traversal. Does anybody have any ideas of how we can change this so we don't need to look at all of the nodes in the tree? We can only look at some of them. Yeah. Yeah, exactly. So the optimization we can make here is is that we don't need to look in both sides of the subtree. So for example, if we're looking for like 35, sorry, let's do 34. We know that if we're seeing 18, there's no chance it's anywhere over here, right? So if we're looking for 34, we can just cross out this entire subtree. Like boom, half our nodes are gone. So okay, and then we get to 35, and we know that that's bigger than the number we're looking for. So there's no way it's in any of this subtree over here. Right, so we're crossing out like a huge number of nodes at each path. So that's a really good thing because now instead of being at O of n, we're at O log n. So, yes. So the question is, why isn't this considered arm's length recursion? Basically, it's not arm's length recursion because everything we're doing is with the node we're currently at. Like all of these if statements have to do with the node we're currently at instead of the node that we would be going to. Like it would be arm's length if we were trying to do something like if node left data or something like that. That's a great question. Yeah. Cool. Anything else we need to do to this function? Let's try running it. Okay, so these all returned false. What happened there? Except for 55, which is our root. What are we missing here? Yeah, return. I heard base case. Close. Okay. Cool. So if we try running it again. Yep, we see, okay, now this matches what we saw before. Okay. So one question we had earlier was, wait, why can't we just do like a post order or an in order? So is there an easy way to do that with this function? Does anybody see a way to do that? Okay. Yeah, so basically you have to look at your current node before you can make a decision about whether to go left or right. So traversals really do matter. Okay. What questions are there about this contains function or like why it works or why it's faster? Yeah. Mm-hmm. The return call here? Mm-hmm. So the question is like, let's say we're currently looking at 87 and the node we're looking for is 10. Won't this code return false? So in that case, so 87 is greater than value, right? Because 87 is bigger than 10. So we would go down and like go to the left child of 87, which is going to be smaller than 87 and like may or may not be 10. So we'll say like, does that subtree contain 10? So it won't necessarily return false because if we ever get to a node in that left subtree that's equal to the value, then it'd return true. So then this would return true? Yeah, so then like this one as large 1 would return true. Does that make sense? Okay. Another cool thing about BSTs are it's very easy to get the minimum and maximum value from the BST, which is nice. Because with our original tree, we'd have to look at every value, right? Just like we have to do with an array or a vector or a linked list, you'd have to look at everything. Does anybody have any ideas where the smallest value of the tree will be? Yeah, all the way at the left. So it's the first node that doesn't have a left subchild. Does that make sense why? Okay. Okay. So, okay. Yeah. There's kind of this idea of, okay, we only need to look at the left side instead of the right side. So you can say return node left. Okay. Right, because we can just keep going down. What is this code missing? Base case, yes. So what's a good base case? Yeah, okay. So here, if we were to do something like, if node not equal to null pointer, we could do something like this, which is what we've seen before, right? But the issue with that is you end up, and like, if it is null pointer, then do something. The issue is like an empty tree doesn't have a minimum value. So we actually need to do a slightly different base case where we say, okay, is my left child null? And then that describes the condition that we were talking about earlier, where we want the first node that doesn't have a left subchild. Okay, and then otherwise, let's write it more. Return node value. Okay. So another example of why BSTs are awesome, because this is only log n instead of n time. Okay. So far we've kind of been cheating because I've just been, we just have this BST that was magically created by linking up these nodes, and like that's great for this one BST. But how can we make other BSTs? Like set also has this adds function, right? So how can we add to a BST? So you can imagine that there are potentially like a lot of different ways you could add. Like, I mean, if you give me a set of values, like there are a lot of different BSTs you can make from that set of values. But we want to find the way, like a good way to add a value to the tree that does the least amount of work possible, because we're really lazy computer scientists. So we want the least amount of changes to the tree as possible. So maybe like talk with a partner and try to figure out like a good place to add the value 14 into this tree. Okay, does anybody have any ideas that they want to share? Yeah. Sorry. Yeah, okay, so the idea is let's make it a child of an existing node in the tree that doesn't have a child already. So let's go down to 19 and then make it the left child of 19. So how did you choose like 19 and not some other node?
14 is bigger than 11, and then 19 have values smaller than.
Yeah, so the idea is, okay, the idea is, okay, so 14 is bigger than 8, so we know it needs to be in the right side of the tree. And it's bigger than 11, so it needs to be in the right side of the 11 subtree. And it's smaller than 19, so it needs to be in the left side of the 19 subtree. And that doesn't exist. So let's just make that subtree equal to the node 14. Does this sound like anything we've done today? Yeah, I'm hearing people say like this sounds like contains, which is exactly right. So the idea is let's like search the tree for the node we're going to put in because sets can't have duplicates anyway. And like if we find it, great. And if we don't find it, well, the place where we were looking and found null, that must be where our node should go. How do people feel about that? Okay. So here, let's just copy the contains code and we can figure out what we want to change here. So, okay. We aren't going to have any like return trues or falses. Should all be add. But what do we want to do if the current node we're at has the value that we're looking for? Do we want to change our tree? Okay, so we can just return. Okay. So then what if, and then, so okay, we have our, go right, go left thing. Here we had another return. So what do we want to do if the node is a null pointer? Yeah. Sorry. Oh, yeah, okay. Yeah, so we can say node equals, new tree node value. Okay? So let's try running this. So I'm going to take away my helpful instabst and add this. Okay, let's try running it. Yeah, so our tree doesn't exist. So what do you think is going on with that? Why did our add function not work? Why don't you talk with a partner for a couple minutes and try to figure out why it didn't work? Okay, does anybody have any ideas of what's going wrong here? Yeah.
The scope of the node variable is just our add method. So we get to the bottom, we add our node to the tree, and then it dies immediately. And so nothing really happens to the original tree that we passed in.
Yeah, exactly. So we kind of have this issue here where this node is passed by value, which means down here when we try to set it equal to something, that change isn't reflected back in main, right? Because it's a different scope because we copied the tree node variable. Right, we've seen this a little bit with linked lists. So what's the fix for that? Yeah, pass by reference. Okay, this is a pretty subtle point. So what questions do you all have on this? Yeah. Well, so the question is, do we need to check if no data is equal to value? So let's try commenting it out. So you just have this portion. Let's try running it. Actually, first I'm gonna run it originally just so we know that this works. Okay, so we got our same tree. But here, so let's try not having this portion. I'm running it. So suddenly our tree only has like one value. Yeah, and so the reason for that is because we're only checking if node is null pointer, like down here, we would end up executing this code. And so we'd lose the rest of the tree. Yeah. Yeah, okay, so the question is, we're doing this pass by reference thing, and like I thought pointers were basically passing by reference already. Like, why is this change not reflected? And the issue is because, so okay, this new tree node returns some value, right? Like 0x ABC. And node originally had some other value, like 0x123. And that 0x123 was copied from main or from the calling function into this function. So this is like a totally separate variable from the previous one, from the one in main. So then we say, okay, instead of having 0x123, we want 0x ABC, which corresponds to pointing to like this node with this value. That's where you get like this issue of it's not actually pointing to the right thing. Right, those changes aren't reflected. Does that make more sense? I think I have a slide about it that make it clearer. So yeah, so the problem is, here we like have this variable node that should be pointing to 45, but it's like completely separate from like the spot in 42 that should be pointing to 45. Does that make more sense? Okay. This is like a pretty subtle point. Okay. So, let's see. Another thing that we generally want to do, we've seen this with linked lists, is you want to clean up your memory, right? You don't just want to leave your tree litter everywhere for the program to deal with until it finally runs out of memory. So maybe talk with a partner about like kind of the general algorithm you might use to free the tree, where we need to free all of the memory of all of the nodes that make up the tree. Okay. So does anybody have any ideas of anything we can use to solve this problem? Yeah, exactly. So the suggestion is we could do a post-order traversal. So why wouldn't like a pre-order or an in-order traversal work here? Yeah.
Because we need to like first check if there's anything on the side like
Yeah, so the idea is we need to like first make sure there's not any children who need to be cleaned up before I like delete myself, because if I delete myself, I lose access to those children, right? And so that's not actually like doing a great job freeing the tree. We just like free the root and nothing else. So this is an example of where a post-order traversal makes the most sense. We won't actually code this here because you'll be doing that on your next homework, but major hint for going to lecture. So okay, we talked about like some examples where pre-order is best with contains. We talked about some examples where post-order is best with free tree. When do you think you'd use an in-order traversal, or why do you think it's called an in-order traversal? Like what happens? Yeah. Sorry, I can't hear you. Yeah, so like a for each loop is a good idea. What were you saying back there? Yeah. So the idea is, okay, an in-order traversal is called in order because the tree, like when you print a binary search tree using in-order traversal, you get something that's in order. Yeah, I don't know where they came up with pre and post though. But so if you are trying to check if your tree is a binary search tree, maybe we should be using some sort of in-order traversal to see if like the elements we're looking at are actually in order. So that's exactly right. And you'll see a problem like that on your section handout. So we have like about 5 minutes left. I could go into how to remove from a BST, but I know you had the midterm yesterday. It's a 3-day weekend, so I'm going to free the trees. So